All right, let's have a look at this practice exam here. So we'll go through how to solve these questions. If you have any further questions, let I or Professor McKinney know. All right, so if a sample is uniform throughout and cannot be separated into other substances by physical means, so if it can't be separated, first of all, if it's uniform throughout, it's certainly not going to be a heterogeneous mixture. And if it can't be separated by physical means, it certainly can't be any sort of mixture at all. And so then it's just a question of whether it's a compound element or both, and there's nothing in here about its chemical properties, and so therefore that substance must be either a compound or an element. An extensive property is one that depends on how much stuff you have, whereas an intensive property is one that doesn't depend on how much stuff you have. So for instance, if I've got a bucket of water at 25 degrees or an ocean of water at 25 degrees, you can describe them both identically at 25 degrees. Same thing with density, that's just an inherent intensive property. Same with melting point, the temperature at which it goes from solid to liquid. Formula weight has nothing to do with how much you have. Mass obviously depends very much on how much you have. It's an extensive property. Mass spectrometry is an experimental technique where we bombard molecules in the gas phase with electrons, and those electrons create ionic species, cationic species of our molecule. It can often result in fragmentations of that molecule, and then we can detect the mass to charge ratio of the species there. So we got a bunch of different mass numbers which correspond to the stable isotopes of boron. The one that will not work is C because there's no charge there. We can't have a mass to charge ratio if there's no charge. So mass spec can only pick up cationic species. 5 moles of hydrochloric acid, sodium sulfide are reacted according to the following unbalanced equation. So that's italicized. It's probably telling us we should probably balance it. So let's just work left to right. On the left side, I got 1 hydrogen, 2 hydrogens. So let's double the hydrochloric acid. 2 chlorines now, none here, 1 chlorine, so let's double the sodium chloride. 2 sodiums, 2 sodiums, 1 sulfur, 1 sulfur, everything is balanced. And so if we got 5 moles of each of these things, but a ratio of 2 to 1, the 5 moles of each aren't going to get consumed. One of them will end up being the limiting reagent. And so if sodium sulfide, for instance, was the limiting reagent, then I'd need twice as much hydrochloric acid. So if I have 5, then I'd need 10. I don't have 10, I have 5. So therefore, hydrochloric acid must be the limiting reagent. We consume all 5 moles of this substance, consume half of that since it's a 2 to 1 ratio here. So 2.5 moles of this are consumed. And again, we can carry that across. We make 2.5 moles of this, and we make 5 moles of that. And since it's the hydrogen sulfide that we're looking for, 2.5 is the answer. A physical process is one where the physical state of matter changes, but not the chemical state. Distillation, we're separating a mixture based on boiling point. That's physical. Filtration, separating a mixture based on solids versus liquids. That's physical properties. Chromatography, process that we're separating a mixture based on the interaction of the components of that mixture with some sort of solid surface or column. That's physical. Evaporation, changing it from liquid to gas, that's physical. So none of them are not a physical process. All right, nomenclature. Complete the following table. Nitric acid. So the nomenclature rule of something that's ic acid must have come from an anion that was 8. And so the 8 version of an anion is the most common one. So that's NO3 minus. I'm not writing minus here because nitric acid takes nitrate and puts that H out in front of it. So now we have CBr4. That's the formula. None of these are metals. There's no acid here. We just have a molecule made up of non-metals. So then the nomenclature rules are we identify the first element and the second element, and then we can specify how many of each we have by the prefixes. But if the first element only has 1, then we don't start it with mono. We're just going to say carbon tetra bromide. The next one, ammonium phosphate. That's an ionic compound. Ammonium, we memorize that to be NH4. and that's a +1 cation. I'm not going to write that down because the formula of the whole ionic compound will have both in such a ratio that the charge goes away. Phosphate, we know, is PO4 3-. So if I got a +1 and a -3, in order to make the charges balance, I need 3 ammoniums to counteract the -3 of the phosphate. So that's that. And now we have the formula of an ionic compound. The anion of oxygen is fairly set in stone to be oxide, which is 2-. So I'm just going to write that down here, kind of going backwards here. Fe is the element iron. That's one of those transition metals in the middle of that periodic table. And it doesn't have a fixed charge, not Fe, iron. And then we can tell the charge of that. Well, if I've got oxide that's 2- and I got 3 of them, that means the total contribution to charge by the oxygen here is 6-. And since there's no charge in this compound, that must mean the total contribution to the positive charge from iron must be +6. And since there's 2 of them, each must be +3. And so the nomenclature, we just put the Roman numeral 3 in parentheses, iron 3 oxide. All right, so now looking at atomic symbols, all we have here is the symbol with some decorations. Now the symbol V corresponds to the element vanadium. You will obviously have a periodic table in front of you. I have one off to the side that you can't see. And so just the number, the symbol vanadium is defined by a particular number of protons, and that is 23. Again, that's just off the periodic table. And then number of protons and atomic number are really the same thing, right? That's the definition of the atomic number, number of protons. So whatever's in this box goes in that box. Now this 51 to the top left of the symbol V is the mass number, so that just goes here. And then from that, we can subtract the number of protons from the mass number, which is protons plus neutrons, and get 28 neutrons. And now finally, for the number of electrons, now we look at this charge of +5, and that certainly means that however many protons I have, I'm going to have 5 fewer electrons, such that that is charged as +5, and that ends up being 18 electrons, 23 minus 5. All right, so for the next one down, can't just start writing in here because I don't know the number of protons, the atomic number, so I don't know the element yet, but I do know the number of neutrons and the mass number. And so the mass number is protons plus neutrons, so if I subtract 18 from 34, I get 16. Again, that automatically goes here. And if I look on the periodic table, the element that corresponds to 16 protons is sulfur, and I can go ahead and put the mass number 34 there, and then charge, if I've got 16 protons and 2 more than that worth of electrons, then I got a 2- anion. Now, we're going to accept either +5 or 5+, or 2- or -2. Doesn't matter either way. All right, so now we got our first math problem. We're looking for the mass of 3.14 times 10 to the 24th molecules of glucose, and we give you the molar mass. So you could just set this up as one-dimensional analysis problem. So you start with what you have, 3.14 times 10 to the 24th molecules of glucose. Okay, so it's molecules, glucose. I think it's helpful to write in glucose even though there's only that one species here. But if there's more than one thing, if you're dealing with a formula, I always like to say moles of what, grams of what, just so you don't unnecessarily confuse it. So we want to get to mass, and I don't have a conversion factor to get from molecules to mass, but I can get from moles to mass. So first I need to get molecules to moles, and we can do that with Avogadro's number. So Avogadro's number is going to be molecules per mole, so I want to put molecules in the denominator, 6.022 times 10 to the 23rd molecules glucose, and that is per mole of glucose. Okay, so we can cancel out molecules of glucose, and now I can apply my molar mass or formula weight of glucose, which is grams per mole. I want moles in my denominator to be able to cancel those out. So I'm going to put 180.16 grams of glucose per mole of glucose. So moles of glucose cancel. The only unit that remains is grams, and so now I can just type this into my calculator. And so I think it makes sense to just multiply everything in the numerator and then successively divide by denominators. So 3.14 exponent 24, that's the molecules, and I'm going to skip ahead to this, multiply that by 180.16, and that's the mass there, equals, and then I'm going to divide now by Avogadro's number, 6.022 times 10 to the 23rd, and I get 939.3928 and so forth and so on. Just looking at this number in my calculator and looking at the sig figs, 3.14, that's 3 sig figs. This is 5. I use 4 with Avogadro's number, so it's 3 sig figs. So I'm going to look at the 10th place and then just round it off cleanly to 939 grams glucose. All right. All right, and now number 9 here. Selenium, an element used in the manufacture of solar energy devices, forms an oxide that contains only 1 atom of selenium and is 37.8% oxygen by mass. What's the molecular formula? All right, so we have a selenium oxide, which means we have SeO. We know it only has 1 selenium. We don't know how many oxygens it has, so that's where we're starting from. All right, but we know it's 37.8 oxygen by mass, and so we calculate percent oxygen by looking at the atomic weight of the oxygen multiplied by how many of them there are. And so we don't know how many of them there are, so that's X. The atomic weight of oxygen is 999.4 grams per mole. I don't need to put the units here because grams per mole is going to be the unit here, grams per mole is going to be the unit here. It's expressed as a fraction, so that's going to cancel. So I'm going to make my life easier by excluding it. So it's the mass provided by the oxygen divided by the total formula weight of this element, which is going to be the atomic weight of selenium times 1. Selenium, as I looked off to my periodic table on the side, 78.971. 78.971. Again, grams per mole, I'm skipping it. Plus, and it's that same X times 15.9994. And again, we'd say times 100% would equal 37.8%, or we can make the math simpler by just saying 0.378. So again, I could say either times 100% here equals 37.8%, but if I divide each side by 100%, I just get that fraction, and that'll just make it easier from here. So now I just got to do the algebra to solve this out. So on the left, I'm going to get 15.9994x equals, and then I just got to distribute this to that side, which means I need my calculator. 78.971 times 0.378 equals, so that'll be 29.851. Now I've got a 3 sig fig number here, which means this 51 is going to be insignificant, but I'll keep it there just in case. And then it's going to be 0.378 times 15.9994, so that'll be 6.0478, say, x. Now again, 3 sig figs, the 7/8 is insignificant. So now I just get the x's on both sides, the one side, by subtracting that quantity, so just negative, and then add it to 15.9994, and I'm going to get 9.9516x, and that's going to equal 29.851. Now, as far as the sig figs here, since I'm doing addition subtraction, it doesn't matter how many sig figs I have, it matters where I am relative to the decimal place. So all these digits to the right here are significant. Only 2 are significant over there, which means that 1/6, which is the 1,000th and 10,000th place, are insignificant. All right, so now I just divide 29.851 by that, and I can do that easily on my calculator by taking or screwing it up in the first place. Let me just do it all over again. 29.851 divided by 9.9516, and I get x equals 2.999, and so forth and so on. Now, we know that there's one selenium. We know that there's going to be some number of oxygens. That number is going to be an integer, okay? So I think I can confidently call that 3, which means that the molecular formula is SeO3. All right, super. Using a mass spectrometer, you measure the abundances of 3 naturally occurring silicon isotopes. What is the average molar atomic mass of silicon based on your calculation? So it's asking for the atomic weight. All right, so we have these 3 different masses in AMUs, and again, AMUs are mappable to grams per mole, and then we have the relative abundance, so we're setting this up as a weighted average. Now, technically, the mass, whether it's grams per mole or AMU of these isotopes, are not exact numbers, but for these purposes, we can consider them exact numbers. If you're given such a thing, I think that's fair. We'll consider those to be your significant digits. If you have any questions about this, let Professor McKinney and I know. Okay, so again, just one big weighted average, and so that is 28 times, and then we're going to turn that percentage into a fraction. Again, it's just easier that way, times 0.9213, and then plus the 29, and that's 0.04783. Okay, again, we're just turning these percentages to fractions by bringing the decimal place over 2 and getting rid of the percent. Okay, and then finally 30 times 0.03087, all of which is going to equal our answer. All right, so again, just some calculator work. 28 times 0.9213. So below we've got 25.7964, 4 sig figs, those are insignificant. 29 times 0.04783, and that is 1.38707, 4 sig figs, those are insignificant. And then finally 30 times 0.03087, 0.9261. All of those digits are significant. 4 sig figs here. Again, we're calling those isotopic masses identical, and now I just add this to the others, plus 1.38707 equals plus 25.7964 equals, and I have 28.10957. All right, so first of all, if you look at the abundances, we've got 28, which is far and away the most common, most abundant, and then we've got some minor ones that are heavier. So because you got 90+%, you know your mass is going to be close to 28, but on the high side because you've got some minor abundances of these others, and so that sort of makes sense there. Now, as far as significant digits are concerned, again, we round it off not by number of sig figs, but by looking at these and looking at how far to the right of the decimal place. So we got 4 places here, 3 here, but only 2 here, which means that we can go 2 places past the decimal for significance. So 28.11 grams per mole. All right, does that make sense? You can't answer me because it's a video, but you get my point. Okay, number 11. Cubane, a component in rocket fuel, contains only carbon and hydrogen. If we combust that mass of cubane in excess oxygen, we get that mass of carbon dioxide, that mass of water. If the molecular mass or formula weight of cubane is this, what's its molecular formula? And we have a couple of molar masses that may prove useful. So it contains only carbon and hydrogen, okay, which means we have that, but we don't know how much hydrogen, we don't know how much carbon, so we're just going to call it XY. All right, so we have masses of carbon dioxide and masses of water, and so the first thing that's going to be helpful is to convert those to moles. But let's just consider, what that formula is going to be. We can't solve it all out. We don't know how to balance it because we don't know what X and Y are, but we do have mass quantities, 1.0885 grams of each of these, 0.2228, right? So we can convert each of these to moles. I'm just sort of diagramming our workflow here using the molar masses or formula weights that are provided. And then given that that's what's created, that'll sort of be indicative of our stoichiometric coefficients here. It'll also tell us how many moles of carbon atoms must have been over here and how many moles of hydrogen atoms must have been over here, because there's no carbon or hydrogen in our other reactant. So that molar quantity corresponds to this. And once we figured out how many moles of water, it's twice as many moles of hydrogen in our cubane. All right, so let's just start off dealing with carbon dioxide. So 1.0885 grams CO2. Okay, and then we have the formula weight here. I'm going to put that on the bottom so that my masses cancel, 44.0095 grams CO2 per mole CO2. Okay, and then the other thing I can turn this into is that because every molecule of CO2 has one atom of carbon, I can just do that as a conversion factor. Okay, so I have 1 mole carbon per 1 mole CO2. So that cancels, the mass cancels, and if I type that into my calculator, 1.0885 divided by 44.0095 times 1 divided by 1, and I get, I'm going to do this in scientific notation, 2.4733 times 10 to the minus 2 moles of carbon. Okay, significant figures. I've got 5 here, I've got 6 here, those are exact numbers. Oh, so I don't even have enough. That's 3, 4, 5, it's going to be 5, but I'll carry an extra one, 3, and that's insignificant. Okay, so same thing with water, 0.2228 grams of water. And then I've got the formula weight, 18.0153 grams of water per mole of water. And then I'm going to have 2 moles of hydrogen per 1 mole of water, because it's H2O. All right, so mass of water cancels, moles of water cancels, and do that out, 0.2228 times 2. Again, just multiply my numerators first, and then I'm going to divide that by 18.0153, and that gives me 2.4735 times 10 to the minus 2 moles of hydrogen. And again, I got 4 sig figs, a lot more than 4, those are exact numbers, so that is insignificant. And so now just looking at these numbers, sig figs aside, yeah, they're not exactly the same thing, but any reasonable person would come to the conclusion that 2.473, that's a 1-to-1 ratio, right? So therefore, carbon to hydrogen is 1-to-1. So that means the empirical formula is C1H1, right? Okay, so now in order to figure out the molecular formula, the formula weight, sorry, we don't have that, but we do have, we do have the formula weight, sorry, 104.15. And so if that happened to be also the molecular formula, we could calculate its formula weight. So the formula weight of CH is going to be 12.0107 grams per mole plus 1.00794 grams per mole. Those are the atomic weights of carbon and hydrogen. And that's going to be 12.0107 plus 1.00794, 13.01864, 6 sig figs, so that's in sig. Okay, grams per mole. Now, that's not the formula weight given in the problem, right? And so in order to figure out, again, just because the empirical formula is this, it could be CH, it could be C2H2, C3H3, C146, H146. We just know they're going to be a 1-to-1 ratio. We can figure out what that multiple is by taking the actual molecular weight, 104.15 grams per mole, and divide that by the empirical formula's molecular weight, 13.01864 grams per mole, and hopefully that works out to something close to an integer. 104.15 divided by 13.01864, and I get 8.00000, and eventually there's some other numbers. Again, I'm just going to go ahead and call that 8. So what that means is that my final answer is C8H8. That is the molecular formula, because you could fit 8 of those molar masses into the molar mass that's given. So what do we got here? 0.322 grams of cubane, excess oxygen. I didn't use that. So you might be taking this test like, oh my gosh, I have this piece of data that I didn't use, and yet, is there anything here that's wrong? Of course not. Just because a piece of information is there doesn't mean it 100% has to go into your problem. Only use what you need to actually get your answer. Okay, last question. Plants sequester carbon dioxide by converting it into cellulose. That's photosynthesis. And that chemical equation can be greatly simplified into that below. Add the coefficients, so the first thing we need to do is balance it, okay? Carbon dioxide and cellulose are the only ones with carbon, 6 carbons, 1 carbon, so let's multiply that times 6. Okay, I'm gonna save oxygen for last because it's an elemental compound, so let's do hydrogen next. I've got 2 here, and I've got 10 there, okay? So that means if I multiply this by 5, then I'm gonna have 10 hydrogens, and I haven't messed up my carbon, right? Carbon's balanced, hydrogen balanced, oxygen, so I've got 12, and another 5, that's 17. I've got 5, which means I need another 12. 6 times 2 is 12, and so that's part A. What mass of water is required for a tree to produce 1.000 kilograms of cellulose by this process? All right, so again, the coefficients correspond to molar ratios or stoichiometric coefficients. I want to know how much water is going to get me to this much cellulose. All right, and so what am I starting with? A mass of cellulose, and I eventually have to get to a mass of water. So this mass of cellulose could be turned into moles of cellulose, which could be turned into moles of water, which could be turned into mass of water, right? That's our workflow. Everything has to go through moles. So let's set this up as a dimensional analysis problem. Before we do that, here's a case where there's a piece of data we don't have that we need, right? This is the stoichiometric ratio, gets me there to there. Here is going to be the formula weight of water, which I don't have, but I did have it on my last question, so that'll save you a little bit of time, right? Formula weight of water, I'm just going to write that down here. H2O is 18.0153 grams per mole. So that saves me one step, but I am going to need the formula weight of cellulose, which is not given. So that's kind of annoying, but hey, what are you going to do? The formula weight is going to equal 6 times the atomic weight of carbon, 12.0107 grams per mole, plus 10 times the atomic weight of hydrogen, 1.00794 grams per mole, and then add to that, 5 times the atomic weight of oxygen, 15.9994 grams per mole, and that'll give me my answer. So 12.0107 times 6, 72.0642. 6 sig figs, all those are significant, rock on. This one I can do in my head, 10.0794, again, grams per mole, and then the last one, 15.9994 times 5 is 79.997. 5 sig figs, more than that, we're good. And then if I add that plus 10.0794 equals plus 72.0642 equals, I get a molar mass of 162.1406. So sig fig wise, I got 4 past the decimal, 4 past the decimal. And since this one truncated my calculator there, but I had 6 sig figs, I can put 6 sig figs here. So that means all of those are significant. How very, very exciting. All right, so we can set this up as a dimensional analysis problem. I'm starting off with the mass of cellulose that I'm wanting to produce. So that's 1.000 kilograms of cellulose. I'm just going to call it cell. Okay, now my molar mass, this is grams per mole, is in grams. So 1 kilogram is 1,000 grams. Cell. All right, so kilograms are now canceling. And so the next step is to apply the molar mass of cellulose that I just calculated. What goes down here? 162.1406 grams of cellulose per mole of cellulose. And now my stoichiometric ratio of 5:1. So for every mole of cellulose, I make or need 5 moles of water. All right, and then finally I have, grams of cellulose, moles of cellulose, and then finally my molar mass of water, which I got from the last problem, 18.0153 grams of water per moles of water. Now moles of water cancel. And then my final answer is going to give me mass, water. So I just need that answer, which is a lot of calculator work. Okay, so 1 times 1,000. Again, just going across my numerators. Times 5 times 18.0153. Okay, and then I'm going to divide that by 1, then 162.1406, and that is it. So I get 555.54, and I'm not going to write down any more digits than I need. Okay, so this has a ton of sig figs, this is a ton of sig figs, exact numbers, so 4, which is my answer, so I need to cut that off at 4, 555.5 grams water, done. All right, so there's your practice exam. Please let me or Professor McKinney know if you have any questions. Otherwise, good luck.